Hello guys, Sir DV again. So today we will be discussing about shear center and shear flow. But before we do a lot of explanation on how shear center and shear flow is, let's start first by recalling some of the basic formula we need in order for us to be able to solve problems on the location of shear center and probably the computation for your shear flow values, not to mention the creation of shear flow diagrams. Okay, some uh, review on perhaps the needed formula in order to solve for shear centers. Of course, the first one we know is the location of the centroid and of course the neutral axis. Also, we have to know how to determine the moment of inertia, and also the computation for shear stresses applied in beams. Okay, so we have done a lot of this in our mechanics, including your RC lectures, moment of inertia, also in mechanics of materials, and in the stresses and beams. Perhaps I'd like uh, you to take note that the shear stress, which is given by tau is equal to VQ over IB, is the reference formula we will be using for plate elements. So this reference formula is now applied on plate elements, and all we need to do is to come up with the same formula for BQ, but this time instead of having a B there, we will be making use of the T to represent the thickness of the plate. Okay, take note that when we have basically a section, let's say I have here a rectangular section, the shear stress is always a maximum somewhere at the neutral axis, and it becomes zero at the surface. Okay, so take note of that this is diminishing. Okay, at the surface. So if I have a direction path of a stress, we can convert this into a shear flow Q by simply multiplying your tau multiplied by the thickness. So this is now our basic definition of what shear flow is. Okay, in application for thin-walled sections, including a semi-monocoque structure and plates, okay, in which the thickness is quite small compared to the width, then I have a plate section here. My shear flow will be primarily directed basically throughout the length of the member. Okay, so my shear flow Q is directed parallel to the length of the member. Or the element. It cannot flow this way, okay? It cannot flow this way because there will be no continuity in this regard. So the flow must be continuous. And since it's very small, the thickness T is so small compared to the length, say L, then the flow perpendicular to the length or through the thickness T is neglected. Okay? So there's no continuity. So in order for us to learn how to draw now shear flow patterns, so let's have here an example section, which is a wide flange section. So as I've told you a while ago, there will be no flow through the thickness. It will always flow only in the direction of the length of the plate element. Okay, so that's the first rule. So if I have here a force, a shear force, inducing a shear stress in this direction, then my flow pattern will start from the end going to a maximum value. So this is now a maximum value. Okay, so my shear flow will start from 0 here, going to a maximum value, and from here, start 0, going to a maximum value there. And then it will flow down. It cannot cross like this. It will flow down up to this portion, which is also a maximum value. Okay, so this is now value is a maximum. So these are now the diagrams for your shear stresses, and it will go back from maximum to a value here, then it will flow back up to a point where it reaches the end phase. Okay, it will be 0 here. So if my direction for shear is horizontal, like this, my shear flow will start at a value of 0 here, increasing up to a maximum value there, and then decreasing up to a 0 value here. Then it will flow again from this point, increasing, then decreasing the value here. Okay, so maybe you will ask me, why didn't it flow towards this value? Okay, actually it will flow here, but this is assumed to be negligible. Okay, so if I will draw now my actual diagram here, so if I will consider this part here, wherein it was considered negligible, I can actually make it more accurate by saying that this will actually flow. Okay, this reaches this point there, it will increase a little bit and then just drop there. Okay. So the value of the shear added by such an element is actually very, very negligible. So the reason for that is because this area is exactly located, the centroid of this area is exactly located at the neutral axis, and therefore there is no moment of area that is developed such that your shear stress will actually increase considerably. So for a channel section, since it is one axis of symmetry, okay, so the shape of the stress diagram, the shear stress diagram, is a little bit different. Okay, if I have here a vertical shear force that will induce the stresses, so I can now start from initially from this face, okay, start with a 0 value here, and then it will increase considerably until a point here which is again the maximum. Then it will go down, it will flow down, increasing from a maximum here to a, a, a value of a maximum here, max 1 and max 2 there. So of course this is much bigger in terms of the stress value, but they are both considered maximum values at the corner, maximum values at the neutral axis. Then it suddenly decreases back to a maximum, then finally decreases into a minimum until it reaches 0. Okay, so if I have a horizontal force directed towards the right, then my shear flow path will start at this point, 0 at this point, then it increases until it reaches a value here which is a maximum, then again another maximum value there, 1 maximum value 2 here, okay, at the neutral axis, then suddenly decreases until it reaches 0 there. And then of course this pattern here will be again repeated until such time that it again decreases to a value of 0. So some draw this diagram to be oppositely directed like this, but maybe it's proper to uh, it is much. It doesn't matter where you put it here or you put it there, but other references makes use of a different uh, sign convention, and as far as the distress is actually okay graphed in this manner, okay, and this here is graphed in this manner, okay. That's why this value here and this value there counteracts with each other. So this at the bottom, 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 top, top, because these are what? These are differently directed. This has the same direction, therefore this must be at the bottom, bottom, okay. Left, right, okay, because they are of the different side, no? While this is only placed or directed in one direction, so it must be on the other side. So it doesn't matter what you want to to follow. It's actually confusing, but I think this is the better way of uh, of representing your diagram for consistency. Okay, so on the next video, I will now show you how to compute for the shear center using some numerical values, and we'll start with a very basic section, which is an angular section. Thank you very much. I'll see you on the next video.